Hi, this is Lab 4 for Physics 2211. Today we'll be looking at oscillations, particularly how energy and oscillations relate and their importance. Today we'll be showing you how energy is constant in a system that has no outside interference, which is the energy principle. And that gives us the equation of total energy equals kinetic energy plus the gravitational potential energy plus the spring potential energy, which all equals 0. Gravitational potential energy and the spring potential energy, because those are the only two forces in the system. This actually, the balance of energies is actually the major reason for the constant oscillation motion we'll see in the video later. And with this, we'll see why the spring and gravitational forces are always changing in order to balance out each other in the video. Why is this needed? Well, it's actually needed in many professions, including physicists and mechanical engineers, and they study this to produce different systems like bungee jumpings and suspensions to make it safer for our consumption. So when we look at the experiment that we actually had, these are the givens that the video was provided for us. Was the length of the spring at time 0 was 0.7 meters, and the mass of the object was 0.402 kilograms, and they gave us a video of the object's motion, which we'll be showing you right now. Alright, so here we are. We have the video of the object's motion, and here we are starting from rest. And as you can see, these red dots will be tracking the object's motion, and you can see the constant circular motion, which is actually the oscillation that we'll be studying today. So in order to replicate the object's motion in a computational model, I need to use some of the given information that we had from the video and find some key aspects of the system. So in doing this, I found the average oscillation time. In this, we used the horizontal motion, so the x-axis motion, and we found the extreme points of each period, and we averaged it out to get the oscillation time average, which was about 1.6103 seconds in this video. We use the oscillation formula to find the spring stiffness, so the oscillation time is equal to 2 pi times square root of m divided by k, and then we can find k from that, which ended up being about 6.1126, and in this we could actually find the initial length of the spring, which is good for the spring force and spring potential energy, and we found that to be 0.05654 meters. And this, we just used this and plugged all the formulas and numbers into the code. So here we are in the code, and here we had to put in the object's mass and initial position. Later on in the code, we put in the spring stiffness and the relaxed length that we had just calculated. This relaxed length is used to find the stretch of the spring at various times in the video, and that is used for spring force and spring potential energy. In fact, here are the energy calculations we have. So 1/2 mass times velocity squared is our kinetic energy. The mass times gravity times the y position is the gravitational potential energy. Spring force, spring potential energy actually is 1/2 times k times stretch squared, and then that's the total energy. And we have the gravitational force right here and the spring force calculated right here to get F net, so that we can update velocity of the object using Newton's second law. And here we recalculate every single iteration to find the stretch and all of the new forces and kinetic energies, and then we find the delta so that we can plot it later. So let's run the program using the actual video's data to compare to our computational model. So here we are with the computational model versus our actual tracked stuff. And as you can see, the blue ball is our computational model, and it sticks pretty close to the actual data that we found, except the actual data is a little bit faster than what we had. Though all in all, the motion is pretty close to the same. Let's just let this run out for a little bit. And there it is. And as you can see, actually a little bit later in our graphs, we'll go in a little bit more in depth, but our x position, as you can see, was behind a little bit throughout it because of our oscillation time, and our y positions were overestimated at all times. So going back into this, here are the discrepancies that I found. As I talked about it earlier, we did have the x value lagging a little bit behind the oscillation, and also our y values were definitely overestimated as far as the extreme points. But all in all, it was pretty close as far as the computational model goes. And here's some discrepancies that we could find. The spring could have gone in the z direction, which is the going back towards the wall or towards the screen. This could definitely result in different position measurements than was actually happening, and could also influence the actual time in which the object was at a full stop for oscillations, which is actually touched on the second point right here too. The oscillations were solely based on the horizontal motion or on the x-axis motion, when actually a full oscillation is when both the x and y motion reach the extreme points at the same time. And also, the video's frames per second was very low, so the results could vary in oscillation times because the frames per second didn't capture exactly when it did actually reach the extremes. Now, what does this lab really mean? Well, it means we kind of understand the energy principle a little bit more, and here we are. The model that we actually created did satisfy the energy principle, as I stated in the equation before. It had to equal 0 total energy in the system, and as you can see on this graph, the total energy is the orange line, which is always at 0, never changing, and this is due to the spring potential energy and the gravitational potential energy being inverses of each other, with help from the kinetic energy to balance out everything. Another thing that we could see is, would it really matter which oscillations we observed? And in this experiment, it definitely does matter which oscillation you observe, as when I calculated what the time for the y-axis oscillation, it was 1.519 seconds and was very consistent. It was always at 1.519 whenever I calculated each oscillation, whereas the oscillation for the horizontal axis needed to be an average, which was 1.62 seconds, and was very inconsistent. And this could be due to the system that we had because all of the forces were horizontal forces.